Hi everyone. Today we're going to look at the standard molar enthalpies of formation in section 5.5. In the previous lesson, we learned how to add equations for reactions with known standard enthalpy changes to find the enthalpy change of another reaction. Chemists have measured and calculated the standard enthalpy changes for thousands of chemical reactions. If you could find the right set of equations, you could calculate the standard enthalpy change for almost any reaction. How can you find these known enthalpy changes? So, chemists have collected and organized data for one specific type of reaction that allows you to generate equations for almost any reaction. This type of reaction is a specific class of synthesis reactions in which the compound must be formed from its elements and not any other compound. So, the standard enthalpy of formation is the quantity of energy associated with the formation of 1 mole of a substance from its element in their standard states. The symbol that we're going to use is delta H naught F. What that naught symbol tells us, which is the circle here, it means that these values are determined at SATP. And if you recall from grade 11 gas unit, SATP stands for standard ambient temperature and pressure, which is always 25 degrees Celsius and 100 kilopascals. All right, and so this represents the third way in which we can determine the enthalpies of reaction. All right, besides using calorimetry and Hess's law. So this information, as I've mentioned, is tabulated, and we can find them in a lot of different reference forms. Our textbook has a very shortened version of this tabulated enthalpy of formation reactions, and it's found on page 320, table 1. So it's good to have it a little bit handy right now. If I were you, I would take it out so that you can reference it when we're going to be working through these examples of how we use this. So if we take a look here in the formation of carbon dioxide, in order to form carbon dioxide from its elements, it is elemental carbon, solid, and oxygen. Those are my reactants. They combine together in a 1-to-1 ratio to form CO2. And so when we write this, it is always written in their standard states. All right. Now, what's also very important to note here, when we calculate and are given these delta H's of formation, they're always in kilojoules per mole. And so we always need to describe it with respect to 1 mole of a substance. Now, the standard elements, states of various elements, is going to be a solid at room temperature. We know that from our previous chemistry courses. 5 of these gases at SATP are found naturally, then that being hydrogen, oxygen, nitrogen, fluorine, and chlorine. Okay, and 2 of them are liquids, so you need to recall that. So these are the ones that we need to know that are gases, and these ones are liquids. All others are solids at SATP that we find on the periodic table. So that's very important to realize. Now, to find the standard enthalpy formation for elements, it has been determined that the enthalpy of formation of any element in its standard form is always going to be 0. All right, so this is very, very important. The delta H of formation of any element in its standard form will be 0. And so that is going to apply to all the diatomic molecules, pure elements, and noble gases that we see on the periodic table. So thus, you will not find these values on a reference table. All right, so that's usually a question that students always ask. What is the delta H of formation of oxygen gas? You won't find it on the reference table. It is assumed and understood that any element in its elemental form will always be equal to 0. Okay, so that's really, really important to remember. So now, how do we write a formation equation? When we write a formation equation, it's always important to write it with respect to 1 mole of that product that we are specifying. So these are the steps that we need to do. Step 2 is you're going to write the elements in their standard states, and then you're going to choose the equation coefficients for the reactants to ensure that we're yielding 1 mole of the product. All right, so that's very, very important to remember. So these are the general guidelines. Let's do an example. So we wish to write the formation equation for liquid ethanol. All right, so if we recall, ethanol's equation, chemical formula, is C2H5OH. So we always want to write that with respect to 1 mole of that product. So products always go on the right side, so I'm going to write C2H5OH L for liquids. Now we need to incorporate all of the elements that are found within this compound. So we've got solid carbon, we have hydrogen gas, which is a diatomic molecule, so we have to write it as H2. It also contains oxygen gas, which is also a diatomic molecule, written as O2 in its elemental form. Okay, and then we write our product, which is the ethanol. Okay, lastly, we need to balance it to ensure that we have 1 mole of this product. So this is where quite often you're going to have fractions as coefficients, which is okay in thermochemical equations. All right, so when we look, we've got 2 carbons, so I put a coefficient of 2 in front of carbon. For hydrogen, I've got a total of 6 hydrogens. 5 plus 1 is 6, so I need to include a coefficient of 3. And then we've got only 1 oxygen, so I need to include a half oxygen molecule. All right, because 1/2 times 2 gives me 1. So this now is my equation for the formation of liquid ethanol. So now, how do we use enthalpy of formation to find the delta H? So instead of using our Hess's law calculations, we take advantage of the fact that the delta H for the target equation equals the delta H of formation of the products minus the delta H of formation of the reactants. So we can write this as a chemical equation, chemical formula. Delta H equals the sum of, this is a Greek symbol that means sum of, okay, so it's sum of the moles times the delta H of formation of the products minus the sum of the moles times the delta H formation of the reactants. So this is a formula that you need to remember. All right, so N is going to represent the number of moles within our balanced equation. All right, so making sure we're getting these mole ratios from the balanced equation that we're trying to solve for. Now you are going to be required, in order to use this equation, you need to be able to reference a table that contains the delta H of formation values for various elements. Like I mentioned earlier, the one on page 320, table 1, is very modified. It's a very small cross section of the thousands of delta H of formation values that are out there. All right, but for our purposes, this is the one we're going to use. All right, so let's take a look at this example. So it says here that we wish to calculate the enthalpy change for the following equation using the standard enthalpies of formation. They do give us a delta H of formation for iron 4 oxide. It's been provided because chances are it's not found in the reference table that's in your textbook. All right, so to solve for this, given this balanced equation, we're going to write our delta H of formation formula, which is delta H equals the sum of the moles times the delta H of formation of the products minus the sum of the moles times the delta H of formation of the reactants. So this is where students make mistakes, is they mix up products and reactants. All right, so that's a very common mistake, so please make sure you always remember that it's always the products minus the reactants. Okay, so I'm going to write out what my products are. So from my balanced equation here, I see that the coefficient represents my moles. Okay, so it's the moles times the delta H of formation of Fe2O4 plus the number of moles times the delta H of formation of CO2. Those are my products, minus, we're going to square bracket here, it's the number of moles times the delta H of formation of Fe2O3 plus the number of moles times the delta H of formation of CO. Sorry, I ran out of space there. And again, it should be a square bracket there. Now I'm going to substitute these numbers into my equation. So I've got 2 moles from the balanced equation of Fe2O4. As well, in the given question, it's told us that its delta H of formation value is minus 1118.4 kilojoules per mole. Plus, for carbon dioxide in a gaseous state, we've got 1 mole of it from the balanced equation. And I have to look it up on my reference table on page 320. And I find that it is equal to negative 393.5 kilojoules per mole. And I'm going to subtract that. I'm going to go on the next line because I've run out of space. I'm going to now subtract my reactants. And my reactants are Fe2O3, iron 3 oxide, which has 3 moles, which is right here. It's got 3 moles. From the balanced equation, and I'm going to look up on page 320 once again, and I'm going to find that Fe2O3 has a delta H of formation of negative 824.2 kilojoules per mole, plus my last reactant, which is 1 mole of carbon monoxide, times its delta H of formation of negative 110.5 kilojoules per mole, all square brackets. All right, so now the tricky part is making sure that I do all of my arithmetic correctly. So I do my first square bracket multiplying 2 times negative and so forth, negative 1,118 minus the negative 293.5, and I get an answer of negative 2,630.3 kilojoules. Noticing that my moles cancel out in all of these. All right, so my moles cancel with moles, moles cancel with moles in every instance here. And then I also work out my second square bracket, ensuring that I'm taking care of all those negatives, and I get an answer of negative 2,583.1 kilojoules. Now I got a negative and negative, folks, so it's got to be positive, so make sure that we do that correctly. And we're going to get a final answer of negative 47.2 kilojoules. Okay, so this is an exothermic reaction. So very important when we're doing this is watching where we're placing the reactants and products, making sure they're on the correct side, making sure that you look them up correctly. One thing to pay attention to is quite often water has two states, gas and liquids. You want to make sure that you're always looking for the correct delta HF formation value, because that's where you can make an error as well if you choose the wrong value. And you need to make sure to be extra careful with your arithmetic, your adding, subtracting, multiplying. All right, so that's it for today's lesson. It's a little bit shorter than yesterday's, so your job is to read over this section and try the homework questions in this particular section. So as a bare minimum, I would definitely do page 323, questions 1 and 2, okay? And then on page 324, you can do at least the first 3 questions would be wonderful. So if you can at least finish as a bare minimum, do 1 to 3, that would be great. But if you have lots of time on your hands and you want to keep practicing, the more you do, the better you get at these types of problems, and those are found on page 324. Good luck, and we will see you in the next lesson.